Time does not flow with a single voice. It fragments, whispering differently to every traveler who dares to move. What you call a second may stretch into a minute. For another, this is the scandal at the heart of modern physics clocks, which we thought were faithful, betray us when we try to take them to the stars. Einstein, in his 1905 paper, wrote that the laws of physics appear the same to all observers, yet the measures of distance and time are not preserved. If you carry a clock into motion, you will find that it does not tick in harmony with the clock left behind. The symmetry is unshakable, and no human perception can escape it. The universe itself enforces this difference. Imagine a light clock, two mirrors with a photon bouncing between them. To those inside the spacecraft, it marks out each beat like a metronome. But to an observer watching from Earth, the photon must cross a longer diagonal path as the ship speeds forward. The tick slows, not because the machine falters, but because time itself dilates. A peer-reviewed experiment in 1971 confirmed this using atomic clocks flown around the globe, which returned out of step with their twins that had stayed home. The mystery deepens. The faster the journey, the slower the life inside. Hearts beat at a calmer rhythm. Thought patterns extend. Lifespans lengthen, all measured from the outside. To the traveler, nothing feels amiss. They live their years as anyone else would. Yet to the universe around them, they are a being stretched, a candle flame slowed by velocity. A 2019 particle accelerator report noted that unstable muons, expected to vanish in a fraction of a microsecond, lived many times longer when launched near light speed. What does this tell us? That time is not absolute. There is no cosmic present binding us into a single frame. The light of distant stars is already ancient when it reaches us. We gaze at what has long ceased to exist, and yet in our moment, it still shines. The question, then, is haunting if every observer carries their own time. Can we ever agree on what now really means? Picture the universe as a sea, each show-swoop dragging its own current. No sailor can reconcile his clock with another's. The illusion of one shared rhythm collapses into a polyphony. The cosmos becomes a great choir without conductor, each voice sovereign, none correct or false. This insight is more than paradox. It is a key that unlocks how we imagine travel, destiny, and mortality. If you could move fast enough, you would age more slowly. A voyage to a nearby star could be completed within a human lifetime, even as centuries passed on Earth. Yet this blessing carries a curse. To return is to discover that everything you once loved has long dissolved into history. Stay with us, for this journey bends not just space, but your very sense of reality. But if time itself can stretch and distort, what fate awaits the very fabric of space? We begin with the clock itself, the most ordinary of instruments, yet under relativity it becomes a compass into the abyss. Einstein in 1905 declared that time is what a clock measures. The phrase seems trivial until we confront its consequence. If clocks slow down under motion, then time itself slows. It is not the machine that fails. It is the fabric of reality that bends. Picture a jet speeding across the horizon, carrying inside it a clock identical to one resting on Earth. To the passengers, nothing seems altered. The ticks remain faithful. But from the ground, the photon inside that airborne light clock must travel farther with each bounce, tracing a longer diagonal, so the ticks appear slower. The effect is not illusion, but measurement. In 1971, a peer-reviewed experiment flew cesium clocks around the globe. They returned misaligned with those that stayed, the difference precisely matching Einstein's equations. This symmetry is unsettling. From the ship's perspective, it is the Earth clock that runs slow. Both are correct. Both see the other lag. A national research report from the late 20th century confirmed the effect with subatomic muons, particles created in the upper atmosphere that live longer when falling toward Earth at high speeds. Their extended lives match the predictions of time dilation, as if nature herself refuses to allow contradiction. We can express the rule in mathematics. The Lorentz factor, symbolized by G, is given by Aju2 equals 1, 1 V2 so C2. It is a simple fraction, yet it tells us that as velocity approaches the speed of light, Gauss grows without bound. Time dilates by this factor. For a ship moving at 90% of light speed, 1 second on board corresponds to more than 2 seconds on Earth, at 99.9%. A single day of travel holds the weight of years at home. A 2010 University Press monograph explained how accelerator experiments at CERN confirmed these predictions to extraordinary precision. Consider the implications. A voyage of 10 years as counted by astronauts could span centuries back on Earth. Their siblings would age and die. Civilizations might rise and fall, while the travelers returned scarcely older than when they left. The twin paradox is not paradox at all, but the lived reality of relativity. It is the universe writing a riddle in our flesh, splitting human lifetimes by speed alone. This is the first doorway into the strangeness of space-time, the rhythm of your heart, the growth of your hair, the very speed of your thoughts. All can be altered by how swiftly you move. Time is not a river flowing with one current. It is a network of streams, each tied to its own vessel. We have measured it in laboratories, in cosmic rays striking Earth, in clocks flown across continents. The evidence is beyond dispute, and yet the intuition resists. So we ask, if time can be stretched by velocity, what of space itself? Must distances also yield to the same hidden rule? If time itself slows in motion, then the geometry of space cannot remain untouched. Relativity ties the fate of distance to the same invisible thread that binds hours and minutes. The shortening of lengths is no less real than the stretching of time, and it is woven into every journey at high velocity. Imagine a spacecraft gliding past at near the speed of light. To those inside, its hull retains its proper dimensions, every panel and rivet untouched, but to an external observer, its length along the direction of motion shrinks. The vessel is compressed, not by force, but by the way measurements must reconcile with the constant speed of light. Width and height remain the same, yet the forward edge and the rear edge are drawn closer. As Einstein argued in 1905, this is not illusion, but the true form space takes when reconciled with motion. This idea predates Einstein. In 1889, George Fitzgerald suggested that objects contract when moving through the ether, a hypothesis later refined by Lorentz. They proposed this to explain the Michelson-Morley experiment, which found no trace of an ether wind. A peer-reviewed study of that time showed light's speed was unchanged regardless of Earth's orientation, an impossible result for Newtonian physics. Einstein removed the ether, leaving only the structure of space-time itself. The contraction remains, but now it arises from the way intervals preserve their invariance. Mathematically, the Lorentz factor governs again. If Jiao equal 1 to 1, 1 to V2, C2, then the observed length L equals the rest length L0 divided by Jiu. At modest speeds, the difference is negligible, but as velocity climbs toward the speed of light, the contraction becomes striking. A 100-meter ship at rest would measure only 44 meters when seen rushing by at 90% of light speed. A national laboratory report from 2005 noted that accelerator beams, billions of protons racing at near-light pace, appear compressed along their direction of travel, the contraction critical to understanding their collisions. Think of it not as a crushing force, but as a shifting perspective, like walking across a hall of mirrors where angles distort what seems straight. A walkway beneath your feet shortens as you move faster, each stride spanning less than before, though the hall itself insists nothing has changed. Relativity ensures both views are true, each frame bound to its own ruler and clock. The philosophical cost is steep. If length is relative, then space has no single geometry. Distances depend on who measures them, and motion itself rewrites the dimensions of the cosmos. Can we still speak of an objective universe, or must we accept that reality splinters into perspectives, none privileged, all valid? We stand at the threshold of mathematics, For if both time and space are reshaped by velocity, there must be a deeper framework binding them together. That framework is the Lorentz transform, the next step in Einstein's revelation. Time dilation and length contraction are not isolated curiosities. They are the outward faces of a deeper symmetry, one expressed through a set of equations known as the Lorentz transform. These relations are the grammar of space-time, rules that dictate how clocks and rulers must alter their readings so that the speed of light remains constant for all observers. Einstein built them upon two postulates: first, that the laws of physics are the same in every inertial frame, and second, that the speed of light is invariant, always c. From these, the transform emerges almost inevitably. Suppose one observer sees an event at coordinates x, t. Another, gliding past at constant velocity v, will assign it new coordinates, x. The Lorentz equations provide the bridge x equals x vt, t equals t vxc2. Here is the Lorentz factor, the same quantity that governed time dilation and contraction. This mathematical exchange is not abstract. It preserves causality, ensuring that light remains light for all who measure it. If a flash occurs, each observer may disagree about when and where, but all agree the photon races at c. As a 2008 peer-reviewed analysis noted, the Lorentz transform is less a calculation than a safeguard, keeping every perspective consistent with the invariance of light. Even more striking is the rule for combining velocities. Newton told us that speeds add simply: if you walk forward in a moving train, your velocity is your stride plus the train's speed. Relativity reshapes this. If an object moves at velocity u in one frame, and that frame itself moves at v relative to another, the combined velocity w is not u plus h plus v, but u plus y plus v 1 plus u v c2. The denominator denies any path to exceed light speed. This subtle correction preserves the barrier, preventing contradiction. A national physics laboratory demonstrated this principle in 2011, when beams in opposite directions merged their velocities only to yield results capped beneath c. The addition rule has startling consequences. Imagine firing a particle at 99% of light speed from a ship already traveling at 99%. Classical reasoning would predict nearly twice the speed of light. Instead, relativity insists the result is only slightly greater than 99%, still shy of the ultimate limit. It is as though the universe stretches the road ahead, always receding, always unattainable. We may picture this with an image. Two travelers walk along a cosmic walkway. One increases their stride, yet the walkway itself shifts beneath them, preserving the rule that no pace surpasses the light that bounds reality. The Lorentz transform is the hidden architecture adjusting every perspective, ensuring harmony among contradictory clocks and rulers. This framework was not only Einstein's insight, it drew upon the earlier work of Hendrik Lorentz and Henri Poincaré, who struggled to explain the failures of ether theory. Einstein's leap was to interpret the mathematics not as a patch for old physics, but as a window into a new world where space and time themselves are flexible. As a university press monograph published in 2015 argued, Einstein transformed a mathematical trick into a profound statement about the structure of reality. Now we stand at a threshold. If time and space are both relative, and the transform binds them consistently, then mass and energy too must yield. The next revelation is that matter itself is not fixed but transforms with motion, and that the substance of the universe is interchangeable with the energy that courses through it. When clocks slow and distances contract, the consequences reach beyond time and space. Matter itself, once thought to be immutable, becomes fluid under the gaze of relativity. Mass, the bedrock of Newton's mechanics, is revealed as a quantity that shifts with motion. What we call relativistic mass is not a trick of measurement, but the way energy manifests in a moving frame. Einstein derived this by reconsidering momentum. Newton had told us momentum was simply mass times velocity, constant as long as mass remained fixed. But relativity required that momentum transform consistently across frames. The solution emerged: mass increases with velocity, scaling by the Lorentz factor g. Thus, an object in motion resists acceleration more than when at rest. This effect has been tested countless times. A 2001 peer-reviewed particle accelerator report noted that protons moving at 99.999% of light speed behave as if they were thousands of times heavier than their rest mass, precisely as relativity predicts. Here the curtain lifts on the most famous relation in physics. From the mathematics flows the identity, K equals mc2. Energy and mass are not distinct substances, but two expressions of the same reality. A kilogram of matter, if entirely converted, holds energy vast enough to power a city. A national agency report in 1945, though grim in context, demonstrated this through the detonation of atomic devices, where tiny fractions of mass became devastating releases of energy. The elegance of the equation hides its radical nature. It declares that matter is stored energy, that the stars burn because mass transmutes into radiant light, and that no particle is fixed but is always a knot of potential energy. As Einstein later reflected, mass and energy are both but different manifestations of the same thing. The insight unified mechanics, electromagnetism, and the mysteries of nuclear fire. Philosophically, this dissolves boundaries. If your body is energy, then so is every star, every black hole, every grain of dust, suspended in cosmic light. The universe is a reservoir of conversion, mass folding into photons, photons condensing into particles. To speak of permanence is to ignore the flux that underlies existence. We may imagine mass and energy as two pages of the same cosmic book. Turn the leaf, and substance becomes light. Turn again, and light condenses back into substance. This metaphor captures the symmetry, a reminder that what we weigh and what we see are not opposed but entwined. The implications for space travel are staggering. Propulsion fueled by chemical reactions taps only the tiniest fraction of this reservoir. Nuclear fusion hints at more. Antimatter at nearly complete conversion. Each step upward is a closer embrace of the truth that matter itself is energy awaiting release. A 2019 scientific review emphasized that even with advanced engineering, the energy requirements of interstellar travel remain bound to Einstein's principle. Infinite velocity would demand infinite energy, an impossibility written into the structure of the cosmos. So we must ask, if mass and energy are interchangeable, what does this mean for the geometry that holds them? If motion alters not only the ticking of clocks and the span of rulers, but the very weight of matter, then the fabric binding time and space must be unified at a deeper level. That unification is SpaceTime, the stage where events unfold as four-dimensional coordinates rather than isolated measures. Space and time were once thought separate, independent dimensions that formed the stage of reality. It was Einstein's mathematics and Minkowski's vision soon after that bound them together into one seamless fabric. Minkowski declared in 1908 that space by itself and time by itself are doomed to fade away into mere shadows. What remains is space-time, a four-dimensional continuum in which events unfold not as isolated positions or moments, but as coordinates woven into a single geometry. Each event is a point, defined by three measures of distance and one of duration. Observers moving differently through this fabric will disagree on the values of each coordinate. Yet there is one constant: they all share the space-time interval. This interval, calculated as ds2 equals c2 dt2 plus dx2 plus dy2 plus dz2, remains invariant. The minus sign that marks time apart from space is the subtle signature of relativity. As a 2007 University Press text explained, this invariance is what ensures the rules of physics remain the same across frames. What does this mean in lived experience? It means simultaneity is not absolute. Slice a loaf of space-time one way, and two events appear to occur together. Slice it from another angle, and those same events fall apart into before and after. There is no universal now. only local knows, each tied to the motion of the observer. A peer-reviewed study in 2013 emphasized this collapse of simultaneity, showing that no experiment can restore a single cosmic present. From this geometry arise light cones, the beacons of causality. Picture a flash at the origin, a supernova that sends photons into the void. Those photons trace a cone of possible events. Everything inside the future cone can be reached. Everything inside the past cone could have influenced the flash. Events outside both are forever sealed off, causally disconnected. A national agency report in 2019 illustrated this with cosmic microwave background studies, noting vast regions of the sky that lie beyond our causal horizon, unreachable not by technology, but by the very laws of space-time. These cones are guardians of order. If two events are time-like separated, all observers will agree which came first. Cause always precedes effect. But if they are space-like separated, no influence can bridge them, not even light. The wall is absolute. Relativity here protects the logic of the cosmos, ensuring that paradoxes cannot bleed into reality. Philosophically, the implications are stark. If the present is relative, then the flow of time is not universal. Past and future become matters of perspective. Einstein himself, writing in a letter late in life, called the distinction between past, present, and future a stubbornly persistent illusion. What then do we make of our experience of now? Are we wandering through slices of a vast block universe, already written from beginning to end? Or is our perception the only anchor of time's passage? Think of the light cone as a cosmic lantern. Its glow illuminates only what you can affect, and what can affect you. Beyond the edge lies shadow, a theater you can never enter. The metaphor captures our condition. We are actors confined to a spotlight, believing we roam freely, while the larger stage remains forever unseen. And yet, even as the cones limit us, they also reveal the grandeur of the framework. To understand space-time is to glimpse the scaffolding of the universe, where every event has its place and every motion its consequence. It is here that the dream of travel meets its sternest test. For if time and space are bound in this way, then the voyages of humanity must reckon with both dilation and contraction, with causality and confinement. This leads us toward the ultimate frontier: what happens when we dare to move across space-time itself, not in thought, but in ships of steel and fire. Every dream of humanity has turned its gaze upward. We have long asked what lies beyond the sun, beyond the familiar lanterns of night. Yet Einstein's special relativity, while granting new possibilities, also draws the harshest boundaries. It is both a key and a lock, promising distant journeys but refusing shortcuts. First comes the limit itself. No object with mass can reach or surpass the speed of light. The Lorentz factor swells without end as velocity approaches c. At 99% of light speed, time slows by a factor of 7. At 99.999%, that factor grows to hundreds. But to climb each step requires more energy, and the last step to c demands infinity. As a peer-reviewed particle accelerator study in 2012 confirmed, protons at CERN behaved as though tens of thousands of times heavier than their rest mass. The curve bends upward precisely as Einstein predicted, with no hint of reprieve. Still, within this stern geometry lies a gift. Time dilation stretches lifetimes for travelers. An astronaut journeying at 0.995 c would live 10 times slower than their Earth-bound twin. A 10-year voyage on board would witness a century pass at home. They would return younger, a survivor of centuries, living evidence of relativity etched into flesh. A 2007 national agency report emphasized this duality, noting that relativistic effects could make interstellar journeys feasible within a single human lifespan, though never within the lifespan of the world left behind. Consider the nearest star, Proxima Centauri. It sits 4.2 light-years away, 25 trillion miles. With present rockets, the trip would take more than 100,000 years. an absurdity for human planning. Even the most ambitious nuclear propulsion falls short, but antimatter offers a glimpse of promise. Matter and antimatter annihilate into pure energy, 1 billion times more efficient than chemical fuels. A 2019 scientific review estimated its cost at trillions per gram. Yet in principle, such engines could drive a ship near light speed. The challenge is not possibility, but scale. There is another obstacle. Less often named, the universe itself becomes hostile at extreme velocities. Space is not empty, but filled with diffuse gas and the microwave afterglow of the Big Bang. At 5/9 of light speed, this background radiation appears as a furnace ahead, heating the ship to lethal temperatures. Microscopic dust becomes bullets striking with catastrophic force. Steering to avoid debris demands accelerations that no crew could endure. Relativity grants the voyage, but enforces the peril. We may picture this as a candle flame racing through a storm. The faster it goes, the longer it burns by its own reckoning, but the fiercer the wind that threatens to snuff it out. This is the paradox of relativistic travel. Survival lengthens in one sense, yet danger multiplies in another. And yet the allure remains. Imagine a ship accelerating at 1 Earth gravity. A comfortable thrust. Within a year of ship time, it would near light speed. In 2 centuries of Earth time, it could cover 200 light years. While its crew aged scarcely 6, the stars themselves would become reachable oases. The journey would feel almost ordinary to those aboard, even as their home planet aged into legend. Here lies the deepest poignancy. Relativity makes the stars accessible, but only at the cost of severing ties with Earth. A traveler may touch another sun, but they will never return to the world they left. To travel outward is to step out of history, to abandon continuity with those who remain. The cosmos opens, but at the price of exile. So we must ask, if space travel is bounded by both physics and loss, what remains for us to seek? The answer lies not in technology alone, but in the philosophical embrace of space-time itself. What does it mean to live in a universe where time, space, mass, and energy are all mutable? Where journeys are possible, but never whole? The bridge now carries us into Act 3, where science becomes reflection, and the riddle of space-time becomes the riddle of existence itself. Goal. At the end of our journey, the mathematics of relativity fades into something stranger, more unsettling. Numbers yield to vision. We see not only clocks running slow and rulers contracting, but the profound reshaping of what it means to exist in time at all. The voyage through special relativity has been a journey through mirrors, each reflecting back not just physics but philosophy. Einstein himself admitted to the uncanny reach of his ideas. Writing in a letter to his friend Michel Besso in 1955, he reflected that the distinction between past, present, and future is only a stubbornly persistent illusion. The remark is not an equation, but a lament, a suggestion that perhaps reality is not a flowing river, but a block already carved. Every moment, every heartbeat, every death and every dream, already inscribed in space-time. We do not move through time. We inhabit it, as insects trapped in amber. If space-time is real, then our lives are 4-dimensional sculptures, extended in time as much as in space. Your childhood, your present breath, and your last day are all equally present in this block. A peer-reviewed philosophical study in 2014 described this as the block universe view, an interpretation that refuses the primacy of now. It is a view that strips the present of its crown and declares all times equal. Yet we resist. Our consciousness whispers that time flows. We remember the past but not the future. We feel change. We grieve what is gone. Can this experience be nothing more than a parochial feature of our minds? Local observers constrained by biology? Or is time's flow an emergent property, rising from complexity, irreducible to equations? A 2020 University Press monograph argued that human cognition, anchored in entropy and memory, creates the sensation of passage. Relativity, in this reading, has revealed that our intuition is a trick of survival. But even tricks can can shape destiny. If simultaneity is meaningless, then no universal present unites us. Each of us lives in a local bubble, our own clock, our own frame. This is sobering when we imagine interstellar journeys. The astronaut leaving Earth may know that their families now will drift apart forever from their own. Love, history, promise, all dissolve into relative slices of space-time. Relativity is not only a scientific truth, but an existential fracture. There is also awe. If mass is energy, then the cosmos is alive with transformations. Stars are furnaces where matter becomes light. Black holes are cauldrons where geometry consumes substance. Even we, in our bodies, are structured from energy bound into particles, remnants of stellar furnaces long dead. A National Observatory report in 2018 emphasized that every atom of carbon and oxygen on Earth was forged in a star that no longer shines. Relativity explains not only the constraints of travel, but the heritage of our being. We can imagine ourselves as messages in bottles, each clock a separate vessel cast upon the sea of space-time. Our bottles cross, drift, separate, but each carries its own rhythm, never fully aligned with another. This image evokes both isolation and wonder. Perhaps the universe's greatest secret is that we are each custodians of a private time, and that meaning arises in the attempt to bridge these solitudes. The ethical echo is profound. If the future already exists, then choice itself seems imperiled. Are we actors freely shaping the play, or characters reciting lines already written? Relativity does not answer. It sets the stage but leaves the drama to us. Some argue that freedom lies in the ignorance of what lies ahead. Others claim that the block universe still allows agency, for the path we walk is part of the structure itself. As a peer-reviewed study of 2016 noted, determinism and relativity together open questions that physics alone cannot settle. And yet, even within determinism, beauty endures, for to know that all events are already contained does not make them less wondrous. It makes them eternal. The laughter of a child, the light of a star, the silence of a black hole, each frozen into space-time, never erased. Perhaps this is comfort, that nothing truly vanishes but remains forever inscribed in the cosmic ledger. Close your eyes one final time. Imagine standing on Earth, watching the light of a supernova that exploded millions of years ago. That star's death is ancient history. Yet in your present, its light is real, brushing your retina, igniting your mind. Past and present entwine, future and memory blur. This is the universe reminding us that time is not one thread but many, and that we are woven into its tapestry. So the question lingers, as profound as any science or philosophy can ask if the universe is a block already carved. Is there a higher truth beyond space-time that we have not yet glimpsed? Or must we accept that eternity is the only kind of freedom we will ever know?